Aloha, this is Roger Brewer and John Peer with the Hawaii Department of Health. This is the first presentation in a series of 4 presentations on the implementation of decision unit and multi-increment sample or DUMIS site investigation methods. Our primary reference for these presentations will be the Hawaii Technical Guidance Manual or TGM. So you hear us refer to this throughout these webinars, and you see a web link here to access the TGM. TGM is in PDF format if you want to download the TGM, or you can also look at it in web-based format. There's 3 primary sections in the TGM that cover DUMIS site investigation methods. Section 3 of the TGM covers systematic planning of site investigations, or how you lay out a site investigation to begin with. There's also a section that discusses decision units. This is something, it's actually a familiar idea, but the term will be new to a lot of people who haven't been doing this in the past. And there's also a small section on report preparation. Section 4 of the TGM discusses sampling theory and the use of multi-increment versus discrete samples to characterize a decision unit. Section 5 of the TGM covers the field collection of soil and sediment samples using multi-increment sampling methods, and also a discussion of field documentation. Section 8 of the TGM covers the use of field screening methods, and especially including the use of a portable XRF to characterize decision units under an MI investigation. So today's the first webinar, and today John Peer is going to review chapter 3 of a TGM, Systematic Planning and Site Investigation Design. So again, discover the basics of how you set up a site investigation to begin with. A lot of this will be familiar. There'll be some new added things that deal with decision unit and multi-increment sample investigations. Tomorrow, then I'll be covering decision unit designations. And once you get the hang of how to collect samples, multi-increment samples, it really comes down to how you designate your decision units in the field to characterize. And John will be discussing that. So a decision unit, you hear this term a lot, is simply the area and volume of soil at a site that you would send to the laboratory as a single sample if you could. That's usually not possible, so you have to collect a representative sample. That's all part of multi-increment sampling approaches. On Wednesday, and I'll come back, I'll be discussing sampling theory and getting into more detail on discrete versus multi-increment sampling methods. And we'll review a field study we did of discrete sample reliability. And this will again address chapter 4 in the TGM. On the 4th day, then John will be back. He'll be discussing the field implementation of decision unit MIS methods. So with that, I'll pass it off to John to start the first webinar.
Aloha, I'm John Peer with the Department of Health HERE office. I'm going to provide you a little background on how our DUMIS guidance was developed over the years, as well as cover basic systematic planning elements for our DUMIS investigation. This includes an initial discussion on selection of decision units, but Roger will be covering in-depth decision unit selection, examples, etc. in tomorrow's webinar, so be sure to join in there as well. This slide depicts the former sugarcane growing areas on our 4 largest Hawaiian islands during the period about 1920 to 1937. This time, inorganic arsenic was utilized as a primary herbicide for growing sugarcane. You can see many hundreds of thousands of acres across the islands at that time were in sugarcane where inorganic arsenic may have been used. In 2004, our office began targeted efforts to investigate soil arsenic contamination issues related to these sugarcane operations. And it was during these operations, these investigations, that we recognized the need for more reliable representative sampling methods than discrete sampling methods that were utilized at the time for adequately characterizing soil remediation for risk assessment. We had In particular, we had one site where we discovered on the island of Hawaii, in which we discovered very extreme variability and heterogeneity across the site. So about a 4-acre site, and depending on where you took a discrete sample, we could have 1,000-fold variation of what that level might be. We realized quickly that if we used discrete sampling methods, especially if we didn't use lots and lots of discrete samples across that site, that our samples would not be representative, and if we chose different discrete samples, we could get a different answer every time that we chose to do that. So we began a search of other alternate methods, and the one we identified and landed on was a sampling method called the GE sampling theory that was developed in the field of geology and also used pretty widely in the field of agriculture and nutrient sampling in agriculture. And fortunately for us, Chuck Ramsey of Envirostat, a consultant, was providing excellent training on multi-increment sampling methods. So that began our efforts to learn a new method and apply a new method in the state of Hawaii. Here are key time periods over the last dozen years, really, in which we developed our decision unit multi-increment sampling guidance. As I noted, in 2004 is when we first were perplexed with the use of discrete sampling to adequately characterize arsenic in sites on the Hawaii island. That led to identifying a new sampling method, multi-increment sampling, and during the years 2005 to 2007, we conducted fieldwork utilizing MIS, as well as provided training on MIS methods through Chuck Ramsey and Envirostat Incorporated to our staff, environmental consultants in the state, and to labs in the state. I would say the major challenge during our initial use of DU MIS methods was the decision unit selection. It's a key part, and how to make the decision unit selection. The decision unit is the area in which we need a representative contaminant level to make a decision, and how we select that for environmental work as opposed to how it was applied in other fields like geology and agriculture. So a key aspect of this is selecting your decision unit, making it relevant to risk assessment, and your risk assessors working on your team, so that the final answer, the average contaminant level that you get for your decision unit, is appropriate for decision making and decisions on the site. In 2008, we developed our first guidance for the use of DU MIS soil sampling and posted it to our online technical guidance manual. This included guidance that was applicable to all chemicals of concern that we were dealing with. Most contaminated sites in Hawaii are small, and the most common contaminants evaluated include petroleum, arsenic, lead, dioxin, PCBs, or mercury. Then in the following years, through 2010 and 11, we posted up additional guidance providing more details on subsurface soil sampling procedures using DU MIS, stockpile sampling, the special issue of VOC sampling, and lab processing of DU multi-increment samples. Finally, in 2016, we posted updates to our TGM guidance throughout sections 3, 4, and 5 in our online TGM. And this included updates and additional examples from the 8 years of experience since we first adopted the procedure in the state, and provided much more detail in which we're trying to present a summary of that additional detail and guidance for you in this series of workshops. I'd also mention that over this time period, we weren't the only ones working on multi-increment sampling in the environmental field, certainly. And even back in 2004, there were some noted documents using the same sampling theory, this G sampling theory, as guidance. I would say of significance is the EPA, the 2003 EPA guidance for obtaining representative laboratory subsamples for particulate laboratory samples. This applied to the laboratory end of sampling particulate samples, but based on the G sampling theory, has an excellent section discussing the G sampling theory in general, and was an excellent document about how to apply this for the laboratory environment. Unfortunately, the guidance was never incorporated systematically into the SW846 methods, so not everybody in many labs never heard about it or were not familiar with this guidance. In addition, the ASTM guidance at that time in 2003, the standard guide for lab subsampling of media related to waste management activities, was also based on the G sampling theory and included significant multi-increment sampling procedures in the lab subsampling protocols at that time. Of special note is also in 2006, the EPA analytical method 8330B, 8330B for explosives was published, and this is the first and only, so far, EPA analytical method that incorporates guidance for use of MIS methods in both the lab and the field collection of samples. The field sampling guidance is provided in Appendix A of that method. And of course, this is for sampling explosives on military ranges. So that was a significant document incorporating the same MIS sampling theory. In 2007, Alaska published draft guidance for using MIS for petroleum samples. So that was also out there during that time period. And another significant document was in 2012, the ITRC published a useful sampling guidance called incremental sampling methodology. So they call it incremental sampling as opposed to multi-increment sampling, but it was based on the same sampling theory and had a lot of the same elements as included in our guidance, although it's not the same in all respects as the Department of Health guidance for the state of Hawaii. The TGM Section 3 covers the site investigation design and implementation elements for an investigation using DU-MIS procedures. And of special note are the sections on selection of decision units. Again, all important decision for environmental work is what are your decision units for making contaminant decisions. So that is unique to this site investigation design guidance. Also, there's lots of examples included in that section of decision units and how they're applied in site investigations. And the DU-MIS investigation protocols also sprinkled through, of course, in the sampling analysis plan element 3.6 here, incorporating the actual sampling procedures doing DUMIS sampling in the field, how to collect samples, how to use proper tools to collect appropriate samples, etc. And then in quality assurance and data quality assessment, importantly with this method is incorporating true field replicates, which generally were not conducted with discrete sampling methods, into each investigation, so that we can get we have site-specific precision data on the sampling for every investigation. These are key systematic planning approach elements for any investigation. You'll be generally familiar with these concepts, typically called the data quality objective. These, especially items 1 through 5, you'll recognize as very similar to the EPA data quality objectives elements. Again, the defining of the decision units is particularly important and unique within incorporating the DUMIS procedure. And in step item 6 of the systematic planning approach here, sampling analysis and collection of samples. Of course, this includes both lab and field procedures and the incorporation of MIS procedures and during your field collection, as well as these same MIS principles and processes for the lab analyses of your samples. The step 7 or 8, which are typically the data assessment elements here. Again, these are similar to what you might be familiar with in any state or the federal environmental investigation procedures. The very unique characteristics of DUMIS are included here in the data evaluation. As I said, we're providing true field replicates, so that's incorporated in this data evaluation in both the field and the lab data. So, more detail on some of the systematic planning elements, beginning on your site investigation and gathering your background information. Phase 1, environmental assessment type data. Just wanted to mention in our investigations here, some of the key elements that have been critical in identifying sites and getting background on sites for our investigations have been the use of historic aerial photos, as well as historic sandborne maps, which are fire insurance maps that were developed in industrial areas that include diagrams that label buildings and uses of buildings. In the example given here, a poison shed is identified on a sandborne map, and then we could go to corresponding historical photo, find that poison mixing shed, and so we can target that for sampling. And then also shown on the map was a cane seed dipping vat in which mercury issues and other fungicide related chemicals could be of concern. So again, the sandborne maps and historical area photos have been critical in identifying problems. The other big factor has been interview with workers. Invaluable to get workers if they're still available. Now, some of these former sugarcane facilities they left the islands many years ago, and workers that were familiar with the sites are quite aged now. They're in their 80s or 90s in some cases, and so it's critical to get people who can still recall these sites if they're available and have worked in the area. Get them in our vehicles and out to the sites to provide background information on the sites to help us select decision units and identify the areas that are targeted for investigation. Conceptual site models are the first step in the systematic planning process. A conceptual site model helps to identify contaminants of potential concern and their associated environmental hazards. A number of those hazards are identified here: direct exposure, vapor intrusion, drinking water toxicity, gross contamination, leaching, etc. Then you'll be generally familiar with these environmental hazards, and the conceptual site model brings those hazards together as an initial step to conceptualize the environmental issues on the site, sometimes referred to as exposure pathways analysis because it includes contaminant migration pathways and site-specific receptors that might encounter the environmental hazards that are identified, and it can an initial site assessment can help demonstrate data gaps that need to be investigated and filled. When evaluating receptors, it's important to also identify current land use, zoning, and anticipated future land use and zoning to adequately assess the site. Here's another sample conceptual site model in a tabular format. As the pictorial conceptual site model, it includes sources, release mechanisms, potential hazards, and whether it's potentially present under current or planned future land uses. In the state of Hawaii, we have several default scenarios that are used in setting our environmental action levels used to evaluate sites once we have representative data for the site. And these are a critical part of the conceptual site models. And these two factors include: is the site located within 150 meters of a surface water body or sensitive aquatic habitat or not? And also, is the site located in an area where groundwater is a current or potential drinking water source or a non-drinking water source? So these factors are default site scenarios in which we have separate environmental action levels designed, in some cases separate EALs for these different characteristics. Another site characteristic that we have different EALs identified for some sites include whether the site is residential use, unrestricted or residential use, and then whether it's commercial industrial use. So there can be different action levels, default action levels for those two different types of use. But as across the board, we initially evaluate all sites for with our unrestricted use or residential use action levels and identify hazards there and then move forward. Here again are the key environmental concerns that we evaluate for setting our default EALs, our Tier 1 EALs, as we call them. And these include, for soil, key environmental hazards like direct exposure, vapor intrusion, gross contamination, leaching. And typically, terrestrial habitats are site-specific, so that will depend on whether there's significant terrestrial habitat on there and typically handled through an eco risk assessment. So that's a little bit separate, but for these other hazards, we have EALs for each of our over hundreds of chemicals of concern developed for each of these environmental hazards that apply to that chemical. And then on with groundwater, the same sort of thing. We have EALs for drinking water toxicity, vapor intrusion, gross contamination, aquatic habitats, as they might apply for a given site. Typically, the hazard then that is identified with the lowest applicable EAL then drives the site in terms of the risk and the assessment. However, some sites can have multiple hazards that are of concern and need to be tracked over time. Our environmental action levels are in our document called Environmental Hazards at Sites with Contaminated Soil and Groundwater. This is in a separate document on our website. The link is given here on this slide. And again, this provides EALs for hundreds of different chemicals for soil, soil vapor, indoor air, groundwater. It's in a easy to use format in a large series of Excel tables that you can navigate in minutes to identify environmental hazards associated with certain levels of contaminants. So once you have representative data, you can then use that data to identify whether our Tier 1 environmental action levels have been exceeded or not. Again, you need representative soil sampling for the site and the DUs you're evaluating for these environmental action levels to be properly evaluated. One last comment about environmental hazards. As I mentioned, some hazards are unique to certain types or families of chemicals, and others have multiple environmental concerns. In some of our most common contaminants like arsenic, organochlorine pesticides, dioxins, PCBs, direct exposure concerns are generally drive the environmental concerns and therefore the decisions on the site. With other chemicals, notably gasoline or diesel-related contaminants or some solvents, multiple environmental hazards may be identified and potentially driving the site: leaching, vapor emission, and gross contamination, depending on the exact chemical in these families. And multiple hazards then need to be tracked and evaluated for the site, and the levels, the average residues on the site may trigger concerns for multiple hazards on a given site. All right, into our site investigation process. Of course, you want to make clear site investigation objectives, and key among those is, has a release occurred? So obviously we're trying to document that whether a significant release has occurred, and if a release has occurred, did it result in residues in your decision units that exceed our Tier 1 EALs. So that's the basic objective in our most investigations in the state. To do that, you need to estimate the lateral and vertical extent of contamination, and then once that is accomplished, you can evaluate the potential environmental hazards associated with those contaminant levels. And then again, that can be used then to make recommendations to optimize any remedial actions that may be appropriate for contaminants that exceed our applicable action limits, and for confirmation of that a site is clean after site remediation has occurred. Again, a decision unit is a specific area and depth or volume of soil for which a representative average contaminant concentration is of interest and will be determined for decision making. Most decision units that we're sampling, sites we're sampling, are very large, so one can't scoop up all that soil for analysis, so you have to take a good representative sample of that DU for making decisions on contaminant levels. We have two basic categories of decision units that we typically employ. One are spill area decision units, or source areas. These are areas where we have some reason to believe there was a specific release. So an example might be a PCB next to a transformer that leaked off the pad onto the side of the transformer, a known release in which you're trying to characterize, and other situations where we have oil spill areas that are obvious and identified and the like. Sometimes there'll be specific operations identified on a piece of property, a former USD site, a former storage site for chemicals, that are identified as these potential spill areas or source areas. These are then identified as specific DUs, generally small. We're trying to focus in on what we know about the site and what we know about past release areas on the site. So these are specifically identified as separate DUs and analyzed. And then oftentimes we're also setting up what we call perimeter DUs. These are basically just areas, additional DUs surrounding the areas that we suspect as the release areas, to sample and ensure that we've captured or are correctly corralled or identified the lateral extent of the contamination. Now, in many spill areas, we also have to focus on the vertical element as well. In some spill areas, we can have significant vertical intrusion of chemicals. So you're also having a vertical element to each decision unit. And on these spill areas, you oftentimes have multiple vertical decision units in that lateral boundary area that you've identified as your spill area or source area DU. The other major category are exposure area DUs, and these are areas in which we don't have a very specific release information, but there may be some suspect of former chemical use on the property. Say it was former ag use, and there may have been agricultural chemicals used on the property in the past, or you're just wanting to sample this property and ensure there are no significant chemical contamination in the area before proposed use. So these DUs are typically larger in size than the spill area DUs, and they're typically set by the land use or anticipated land use. A good example is the size of the residential lots that might be going into an area. So the exposure area DUs might be the size of the residential lot, say in Hawaii anyway. That could be 5,000 square feet or larger, depending on where you are. Or it could be even as specific as to the area of the backyard or in existing residential areas that are accessible and used by the residents for in their yard over time. So they're site-specific, generally based on the land use, and used to confirm non-suspect areas as well as to check out areas where you might have some suspicion that there could have been some chemical use in the past. Some additional decision unit basics. Again, the decision unit is the volume of soil or sediment or other media you would send to the lab as a single sample if you could. Now, as you know, in most cases that's entirely impossible. So we have to take representative samples to get a representative average of the contaminant in that decision unit. The shape, area, and depth of the DUs are site-specific. These illustrating on the left-hand side here are some source areas. This might be a good example of a transformer, a PCB transformer used to being on a pad, and there was a known or suspected leak off to the side of the pad. So this is a source area specifically targeting the area where the leak would likely have occurred. And then up here is a pond area where there was a release of contaminants suspected. So again, that would be a specific targeted area. Where there wasn't a specific target area, say this is a portion of a yard in which we're trying to confirm the absence of chemicals, or there may have been some suspicion, but we don't know where exactly, we'd stake out a larger DU in that area, or select a larger DU based on the yard area being used as the selected DU. Here's an example in a commercial industrial environment where the DU is selected in the area in which the workers would utilize during their work and operations. They basically would be roaming across that entire area to potentially get exposed to any residues in the soil. So that's a larger DU. It provides for, or we're targeting what the average contamination is in that area that's utilized by employees at that commercial site. Again, if there's specific sources like this, they're always analyzed separate as a source or spill area DU. If there's no specific source identified, we generally have larger DUs that are based on the land use type present. So just this slide provides a basic visualization of our DU process in which we're identifying the target. In this case, it's an agricultural field area. We're laying out systematic random increments across that decision unit, and we typically have 30 to up to 100 DUs depending on the chemical, the amount of heterogeneity expected on the site, etc. These 30 to 100 increments are placed throughout the DU, stratified random locations, and in certain DUs, or at least a representative number of the DUs on a given site, we're collecting triplicates. So we're going back in at separate random locations, not these same ones. We don't do co-located samples, but we'll take separate stratified random locations located across the site, collect another 30 to 75 increments, and do that again. So we have triplicate independent lab replicates on a site-specific basis on every investigation to evaluate error or the amount of precision in our sampling technique and defend our decisions. We can say we can go back in, sample separate stratified locations, and get the same results within a reasonable variability. We typically are shooting for a reproducibility within about 35% for replicates. So if we get if our replicate data shows a relative standard deviation on the triplicate data of less than 35%, then we call that good data for environmental sampling and utilizing that RSD average for making decisions on the site. Another key part of the DU-MIS is that the samples are much different than the discrete samples, and they're very large. We're collecting these 30 to 50 increments. We're usually collecting 20 to 50 grams at each increment, so we're ending up with 1 to 2 kilogram samples. So these are large samples that you're going to be collecting and sending into the lab, as opposed to, say, just 20 or 30 grams or a small 6-ounce jar for the old discrete sampling method. The larger samples, many increments, larger samples, helps us get a much more representative sample. Also, the laboratory has to follow through on the whole multi-increment sampling method. So the laboratory is typically taking the sampling, drying it, air drying it, as long as these are non-volatile contaminants. They're air drying it and then sieving it to less than 2 millimeters, which we define generally as soil-sized particles. And that keeps the evaluation from one site to the next on the soil-sized particles. We also need to know the maximum particle size for the lab to select their subsampling mass and reduce laboratory error. So for our less than 2 millimeter soil samples, the lab needs to then subsample at least a 10 gram subsampling mass out of that bulk 1 to 2 kilogram sample for analysis. These are subsampled in the labs, very similar to how we sample them in the field. The lab will, after drying and sieving to less than 2 millimeters, will spread this sample out very thinly and take their subsampling increments at 30 or so locations across that spread out sample to make up their 10 grams, 50 grams or more of subsample that are then used for the analyses. This slide illustrates different exposure area decision units and notes that your decision units can vary depending on your site objectives, and the size of those decision units can vary, although the principle of sampling and how we sample those, choosing the number of increments across that DU, etc., stay largely the same and are independent of the size of the decision unit. Again, whatever decision unit size is chosen, whether it's a large park or neighborhood size, if you're sampling 50 to 100 increments in here, you'll get the average level of contaminants in that park or neighborhood, and in some cases that is the question that you're starting with or are working with. In other cases, you're targeting smaller DUs like yards for residential, evaluating residential exposures, and even smaller areas in some cases like the perimeters of buildings or a backyard area in a yard or a sandbox where a kid is playing. Again, you'd apply the DU sampling methods similarly to representatively sample the sandbox as you would in a park area. For ecological risk assessment, your decision unit may very well be the home range of a certain bird or reptile or other critter, and your final analysis will be based on your ecological risk based on the home range of that animal. As you can see, the sizes and shapes can vary significantly and are site-specific. So here's an example of applying the DU on a real site. This is in Hilo on the Hawaii Island. This was a former wood treatment site and arsenic and dioxin were the key contaminants on the former wood treatment site. Outlined in red here was the main former wood treatment site. So this was treated as a separate decision unit because we're looking at arsenic and dioxin across the main area that was involved in the wood treatment area. And then we've got smaller DUs that are perimeter type DUs around that to try to confirm that our arsenic and dioxin residues haven't spread out of the area that we suspect they're in, and doing separate DUs on, around them to ensure that we've adequately determined the lateral extent of the contamination. Many of these DUs were surface areas DUs where we expected the contamination, but we also generally do at least one subsurface decision unit to ascertain that the primary contamination was restricted to the surface area. Now this site also entailed a railroad line that came in across the site, and so these somewhat larger DUs were set out bracketing the former railroad right-of-way, and again perimeter DUs set up outside the right-of-way to bracket or try to confirm that we've adequately captured any contamination that may have been in the railroad area. This small DU designated here was an oil spill release that was very small and identified a specific area. So again, that was a source or spill area DU that was done separately and separately analyzed. And then the rest of the property in which there was no obvious suspected contaminants and was used for general warehousing and other operations was a larger DU, and these can oftentimes be up to an acre or so in size, and so this was analyzed as a separate exposure area DU in a larger sample size. So this is putting together for a more complex site different DUs to characterize the different environmental the contaminants as well as anticipated environmental concerns on the site. For very simple sites, one residential yard, of course, you'll have just a single, could have just a single decision unit plus replicates if they're applicable. And but for more complex sites, you might have a number of DUs, in this case more like 10 or 15 to cover the entire site. And they're in more complex industrial sites like former sugar mills and the like, you may end up with 20, 30, 40 different decision units to characterize the range of chemicals and operations that used to occur on a major industrial site. Another type of decision unit I've been talking about are perimeter decision unit. Here's a good example of a perimeter DU around a building. We'll oftentimes target older building footprints or pads here around the edge of the pads where lead paint that used to be used on the building may have sloughed off and fallen to the area outside the building foundation. Termaticides, if these were former wooden buildings, are oftentimes treated with chlordane and other chemicals along the foundation and or underneath the building if it was accessible. So these would be the foundation area would be targeted for that reason. And in some cases there was weed control around the edge of the building. In the old days, arsenic was used for weed control, so we typically look for lead, arsenic, and termaticides or the organochlorine pesticides in investigations of buildings. And then we'll set up these perimeter DUs around the targeted area to sample and ensure that we've adequately captured the lateral distribution of a significant contamination areas. So we'd be looking for these perimeter DUs to be clean or under our action limits, and suspecting that these DUs along the perimeter of the building might be contaminated with our suspect contaminants. Here's just an example set up in a drainage canal. So you might be sampling in ditches or shallow sediment in drainage canals. This was a former sugar mill discharging into drainage canals, and we're wanting to look for mercury or other chemicals that may have been used in former days in the sugar mill in these drainage canals, setting up an initial DU closest to the mill where we might suspect some of the majority of the contamination may have remained, and then additional DUs further down gradient to look for residues along the drainage canal. And here's an example of applying our DU-MIS principles to a subsurface area. Subsurface areas are in any scenario are more difficult to sample than surface samples, which we can usually access with hand tools. These are usually accessed with push devices, coring devices, the like. But the same principles apply. A DU is a given volume of soil. We typically have a surface soil increment, and then subsurface decision units below that. And we're designated the size of these decision units. Now it's site specific, so in some cases these vertical depths of these decision units could be several feet long, whereas a surface increment is typically fairly shallow. These subsurface increments could be 2 to 4 feet, something like that in some cases, depending on the chemicals of concern and site-specific elements. So again, we have here in this example 4 different layers. This is just part of the cores shown, but you'd have 30 cores through the DU, and for each of the layers there'd be the core would be collected through the layers, cut into your different vertical depths, and then all these DUA layers would be combined into one sample, one large multi-increment sample. If the core is large, these oftentimes have to be subsampled to add to the sample that goes to the lab, subsampled in the field because of the mass is so large. But then all the cores from this increment would go into this DU sample and the like. There'll be much more, as we've mentioned before, tomorrow on DU examples and applying DU and sampling in a variety of DUs, including these subsurface DUs. Here's another example where we typically have subsurface DUs as well as surrounding surface DUs, former pesticide mixing. In these areas, gross contamination, spills on the ground all the time, typically result in deeper contamination, and so more vertical delineation near the tanks. This oftentimes we've found significant contamination, arsenic and dioxin down 10 feet depth in some of these former pesticide mixing areas. But as you go away from the pesticide mixing areas, it tend to be surface runoff and more shallow contamination. So we're typically looking at a shallow surface area and then a subsurface decision unit to kind of define and delineate the contamination away from the major spill area here on this site. And another example here is given for sidewalls of an excavation, and obviously a UST or some sort of a contaminant excavation is a good example for this. So if you're suspecting leaking primarily at the bottom of the DU, out of the bottom of the tank or source, then obviously your bottom area of that excavation would be your decision unit. Again, we would place stratified random increments across this DU and get a good representative average of the contaminant level across that entire floor of the excavation. If you had side vents or suspected contamination release and going out to a side, you could then make that a separate decision unit on your sidewalls, or if you had no suspicion on the sidewalls, perhaps combining all the sidewalls into one decision unit, or separating them out into one and two, three, or four sidewall decision units, depending on site-specific information. And a final basic example I'll give you is our stockpile decision units. So this is an area in which trucks had excavated an area in which was later suspected of contamination, dumped these stockpiles in many, many piles across this large former agricultural area. And so to sample those areas, those stockpiles were knocked down for access to the area and sampled in an area that was based on the planned reuse of that soil. So in this case, in this particular example, the amount of soil or the size of the DU is based on the amount of soil that would go in a worst case scenario in the top 6 inches in a residential lot. So that was the DU volume, was 6 inches deep. So that each one of these then were sampled for that DU size and depth to characterize the stockpiles that were dumped here. We have, in our guidance, we have default volumes for stockpiles. Again, as I mentioned, they're based on presumed reuse of the soil. So in a worst case scenario, we assume that a stockpile could be utilized in a small residential lot, 5,000 square feet, spread to a depth of 6 inches. So that would result in a corresponding DU volume of about 100 cubic yards. For more intense uses, commercial, industrial, or high-density developments, that those assumptions on thickness and acreages increase. Therefore, the default DU volumes that we approve for stockpile sampling can be larger. And a final example of a considerable challenge in sampling is sampling of very large areas. And we've had a number of examples here in Hawaii where former ag land was purchased, several thousand acres, and was to be developed into residential or mix of commercial and industrial residential uses. Therefore, we're faced of the daunting task of trying to characterize contamination over these very large areas and making reasonable decisions on the contamination of the property and strategies that we can adequately try to represent this. And then, as the properties increase, we have less and less insurance, or there's less of the total property being analyzed as you go larger and larger here. So we're adding in, as we get above 118 acres, we're adding in what we call a baseline investigation, which is an initial investigation where we're breaking up the property into large neighborhood size areas and analyzing those first, doing representative samples for those neighborhood areas to look for broad patterns of contamination, large contaminated areas, as well as looking at certain contaminants that might pop up in those large areas to include in the investigation. Again, phase one is conducted in every case, and if that phase one reveals any area where there's a source or spill area, those are analyzed totally separate as separate DUs in addition to the DUs we're talking about here in the baseline investigation or the 59 randomly located. So in this large area, we're doing both a baseline investigation, and then within those areas, we're, as above, we're locating 59 randomly located areas, 1 acre DUs, again, to look for contamination at that scale. And finally, in the very, very large sites, and these are pretty uncommon, but they do come up occasionally, we'll do both the phase 1 ESA to look for source area, spill area DUs, the baseline investigation, so looking at a number of DUs, neighborhood size across that property first to look for wider scale or larger scale contamination and contaminants of concern. Then we'll pump up the randomly located 1 acre DUs to 90, so we're getting a little bit better coverage as we go up to this larger acreage. So moving right along in our investigation procedure here, our sampling analysis plans. Of course, these are similar to sampling analysis plans that have been used for a long time in environmental investigations, with the exception that we're incorporating the DU-MIS approaches, so they'll be incorporated and included in your sampling analysis plan. So we're expecting maps of DUs that have been selected, lists of chemicals of potential concern for those DUs, lists of the size of those DUs, the number of increments that are going to be used in those DUs, the sampling tools that will be utilized to make sure that correct sample shape is being collected, which is a core shape is what we're shooting for. And then, of course, good maps summarizing the location of the DUs and tables with DU-specific information, the size of the DUs, the depth of each DU, the volume, number of increments per sample, etc. So we'll have all those details and can review that before the actual sampling occurs and make sure that it's in line with our DU-MIS investigation procedures. And of course, the sampling plan includes a summary of all chemicals of potential concern, what environmental hazards are associated with those chemicals, and are listed default Tier 1 EALs for those chemicals and environmental hazards, and the laboratory information, lab analysis method, lab detection limits, and the like. Now, because it's critical that the laboratory follow through with the MIS processing and subsampling procedures, we also, it's very important that the lab share their MIS SOPs for processing these large multi-increment samples for us, and that those details are also included in the sampling analysis plans. In data quality assessment, again, a key part of any environmental investigation, and has been for a long time. A key part of this is that we have true field replicate data, triplicate samples on every site-specific investigation to evaluate error and or precision, however you want to talk about that, in the sample data, and ensure that we've got good reproducibility, that we're getting the right average level of contamination in the DUs that we select. Now, this is, we don't do replicates in every decision unit. As a practical basis, we take sort of a batch approach like a laboratory will do. As you know, in laboratories, they'll do 10% or 20% of their samples, they'll do the QC and replicate data on to evaluate. We'll take a similar approach in the field with these replicate data, and we'll do at least 10%, but that has to be in a similar soil type, similar characteristics, or if they're different, then replicates have to be conducted in those different scenarios as well. If you have different chemicals, you need replicates to represent all the different chemicals in different DUs and the like. So initial 10% could be more depending on the site-specific information. And this is a key important part of our multi-increment data. We've got the data. We'll provide site-specific data on every investigation on the precision of the data so that you can defend this data and show that in your data quality assessment. And the lab does the same thing. They're taking replicates on their subsampling, potential subsampling era. They have to get a representative sample out of that 1 to 2 kilogram sample that you send to the lab. So that's a challenge for them. Like I say, they have to do multi-increment sampling in the lab to do that, and they'll do 2 or 3 replicates of that in the lab to ensure that the replicate data meets their laboratory criteria for good or precise samples. And we always like to see the final data, the concentrations of chemicals of concern, located or put on a map with the DUs. So you'll be pointing to the DUs and pointing to those where the chemical concentrations are over our applicable action limits. So we can zero in on a map on both the DUs and the data that's significant for any further evaluation. Site investigation reports include your initial DQOs for the site, and most notably information on the selection of decision units, tables with details on those decision units, the size, the depth, the number of increments, etc., so that we can, the department checks these reports and make sure that the representative sampling methods were employed and that the final data is representative of the site. As I mentioned, figures locating the DUs, locating information within those DUs are a significant part of those site investigation reports. And in the data assessment element of that will be, it's critical to include an assessment of the field data as well as the laboratory replicate data as part of your data assessment. And in our state, the final step in our site investigation process and reports is what we call our environmental hazard evaluation, in which the representative sampling data is compared with our environmental action levels, and any exceedances of our applicable levels are identified, and then go from those, any exceedances, what conclusions are made in terms of the need for any additional investigation or remediation for the site. We have a separate TGM technical guidance manual section on environmental hazard evaluation, and a separate document, as I mentioned earlier. This is TGM section 13, and it's important that we have this EHE report for all sites. And so it's typically included as part of the site investigation report, but could be a separate document. Again, the EHE compares the site data, the representative site data, to our action levels, or if we have site-specific risk assessment information, compares it with that and identifies potential environmental hazards, and then makes a conclusion in terms of need for additional site investigation, or whether the site will be determined below action levels and no further action necessary. Okay, thank you for your attention here. I wanted to remind you that tomorrow will be our next short webinar led by Roger Brewer, and that'll be an in-depth discussion on the designation of decision units, presenting lots of examples, and so be sure and stay tuned for that.